Howdy. This video is about writing expressions for reaction quotients and equilibrium constants. Reaction quotients are important because they're used to monitor the reaction. Equilibrium constants are important because we can use them to determine the concentrations at equilibrium. By comparing a reaction quotient with an equilibrium constant, we can determine if the reaction will produce more reactants, or will produce more products, or is at equilibrium. After watching this video, you should be able to identify the similarities and differences between reaction quotients and equilibrium constants. You should be able to write down expressions for reaction quotients and equilibrium constants. You should be able to determine the reaction quotient for a reaction. You should be able to determine how a system will reach equilibrium. And given the relative values of Q and K, determine if the forward or reverse reaction is faster. And you should be able to determine concentrations at equilibrium. And so you can determine, or you can consider equilibrium kind of using this diagram. And so the y-axis is the Gibbs free energy, potential energy. The x-axis is the reaction quotient. Now this line here represents the potential energy. And so in this case here, our products have higher potential energy than our reactants. Now the potential energy will be a minimum, typically somewhere in between, because when you have a mixture, you have an increase in entropy, and that will make the system more stable. Now the position of the system is represented by the red dot here. We can imagine as an analogy, say the line is a valley and the position is represented by a boulder. And so no matter where the boulder starts, it always ends up in the minimum. And so we can think about, if we start with all reactants, eventually the boulder rolls down until it's here. If we start with products, eventually it rolls down until we get to there. No matter where we start, the boulder always ends up at the minimum. And so in this analogy, both the reaction quotient and equilibrium constants represent the position of the boulder, but the equilibrium constant only defines the final position. The reaction quotient defines the position at any time. And so for the equilibrium reaction quotient, it's products of reactants, coefficients become exponents, pure solids, pure liquids do not appear. Now, if you look at this reaction, whenever we have an equilibrium system, we usually use this double arrow indicating that the forward reaction can occur and the reverse reaction can occur. But even though either the forward or reverse reaction can occur, we always define the stuff on the right as products and the stuff on the left as reactants. Now we can write down the expression for the equilibrium constant, and it looks exactly the same. Pure solids, products over reactants, coefficients become exponents, pure solids, pure liquids do not appear. And again, they look exactly the same, but K only defines the minimum position. It's a constant for a specific reaction at a specific temperature. Q can define the position at any time. And if Q equals K, then the system is at equilibrium. If we look at a couple more examples, here we have antimony pentachloride can go to antimony trichloride plus chlorine gas. And so again, products over reactants, coefficients become exponents, pure solids, pure liquids do not appear. Looking at this example, products, the stuff on the right, and the coefficient 5 becomes that exponent, coefficient 6 becomes that exponent, over reactants, and that 8 comes down there, pure solids, pure liquids do not appear. Now in these two reactions, we didn't have any pure solids or pure liquids, so we didn't have to worry about it. If we look at this reaction, we have liquid water going to gaseous water. Now we think products of reactants, we'd write it this way, but pure solids, pure liquids, if you have an S or an L there, should not appear. And so the properly written equilibrium expression is just K is equal to concentration of water vapor. If we look at another example, here we have sodium chloride solid going to sodium ions aqueous plus chloride ions aqueous. And so if we write down products over reactants, we would write it this way, but again, pure solids, pure liquids, when you have an S or an L, we treat them as if the concentration is not changing. They have what's referred to as an activity of 1. And so the properly written equilibrium expression does not include solids or liquids. So if you have an S or an L. Now aqueous means dissolved in water, and it's not a pure liquid. And so whenever you have aqueous compounds, they always do appear in equilibrium expressions. And again, the importance of the equilibrium expression is it enables us to determine the concentrations at equilibrium. So for example, If we're told about this equilibrium, we have N-butane going isobutane and has the equilibrium constant of 2.5, we could be asked, if at equilibrium N-butane is equal to 1 mole per liter, capital M is molarity, which is moles per liter, what is the concentration of isobutane? And so we can take this expression, and if we multiply both sides by N-butane, we'll get isobutane concentration equals N-butane concentration times K. And so using that, we can see that isobutane would have a concentration of 2.5 moles per liter. And so again, equilibrium expressions enable us, or equilibrium constants enable us to determine concentrations at equilibrium. If we look at another question, if at equilibrium N-butane is 2 moles per liter, what's the concentration of isobutane? We do the same thing. Isobutane is going to be equal to N-butane times 2.5. And so this tells us that isobutane would be 5 moles per liter in that case. And so again, the equilibrium expression tells us the ratio. So this tells us that the ratio of isobutane over N-butane at equilibrium is 2.5. It does not tell us the absolute concentrations. To determine the absolute concentrations, we have to have more information. Now, because K is greater than 1, that means that the products are more stable than the reactants. And at equilibrium, we should have more products than reactants. Now, no matter initial concentrations, the concentration at equilibrium has to be consistent with the equilibrium expression. So no matter what your concentration of N-butane is, the concentration of isobutane has to be 2.5 that. So equilibrium constants have to be followed when the system reaches equilibrium. Now we could also be asked, if the concentration of isobutane is 5 moles per liter and the concentration of N-butane is 1 mole per liter, is Q greater than K, less than K, or is Q equal to K? Well, so we have K, we're told it's 2.5. We have to determine Q, which is isobutane over N-butane. So 5 divided by 1. So Q should be 5. And so that means Q is greater than K. Now, how will the system reach equilibrium? Well, if Q is greater than K, that means we're on this side. Remember, the x-axis is Q. And so if Q is greater than K, we're here. All the way here is just products. And so products will convert into reactants until we get to equilibrium. And so it would also say that the reverse reaction will be faster than the forward reaction. Both reverse reaction and forward reaction always occur. If you're Q greater than K, it means the reverse reaction will be faster. That's how you can go to the left. If Q is less than K, the forward reaction will be faster. That's how you go to the right. And if you're at equilibrium, Q will equal K, and that's why the concentrations will be constant. Now, in another video, we'll actually be able to calculate the concentrations at equilibrium, and we'd see that the concentration at equilibrium for N-butane would be 1.7, isobutane 4.3, if their initial concentrations were 1 and 5. Now, I really like these graphs. I think they're really helpful in representing chemical systems. Now, we've talked about delta G naught. That's the standard change in Gibbs free energy. That's pure products minus pure reactants. And so that's this distance here. Delta G is the slope of the line. And so delta G changes as the reaction proceeds. Now, because it's the slope of the line, when you get to equilibrium, the slope is 0, and so delta G is 0 at equilibrium. And so delta G equals delta G naught plus RT natural log Q. And again, that superscript here means standard conditions. No superscript means non-standard conditions. But it's a fairly important equation. You should know everything it symbolizes. Remember, R is the gas constant, T is temperature in Kelvin, and again, Q is the reaction quotient. And remember, you can also do products minus reactants. And so delta G naught equals the products standard Gibbs free energy minus reactant standard Gibbs free energy. And for standard conditions, you're just using pure solids and pure liquids. And you can get those values typically in a table. If you do non-standard conditions, you'll need to actually calculate the non-standard Gibbs free energy. Now, if we think about what this means, If the free energy of the products reactants are the same, then delta G is equal to 0, and so the system is at equilibrium. If the products are higher in free energy, meaning they're less stable, then that would give us a positive delta G, and so the system will want to convert products into reactants until we get to equilibrium. If the reactants have higher free energy, then the delta G for the reactants would be larger, and your delta G for the reaction would be negative, and so systems are going to convert reactants into products to get to equilibrium. And so systems reach equilibrium just trying to get to the most stable configuration. And so we saw that delta G non-standard equals 0 at equilibrium, and Q equals K at equilibrium. And so if you plug in K for Q in this equation, and 0 for delta G, we get this equation down there. Now if we subtract RT natural log K from both sides, we see that delta G naught equals minus RT natural log K. And so this is kind of cool. What this tells us is that given delta G naught, we can actually determine K. Given K, we can determine delta G naught. And so if we're given K, we need delta G naught, we could use this equation here. Now if we divide both sides by minus RT, we get this. Now if we want to get rid of that natural log, we take everything to the power of E. And so we get K is equal to exp of minus delta G over RT. Now this is just another way of writing K is equal to E to the power of minus delta G over RT. Now it's kind of cool. If we look at this equation, remember K is a constant for a specific reaction at a specific temperature. Delta G naught is also a constant for a specific reaction at a specific temperature. So these guys do not change unless you change the temperature or the reaction. Now if we look at this equation down here, we saw Q changes as the reaction proceeds, and so that means delta G also changes as the reaction proceeds. And so delta G naught is again products minus reactants, and delta G non-standard is just the slope of this line. Now if delta G naught is positive, that means the products have higher potential energy than the reactants. The products are less stable, the reactants are more stable, and so we'll have more reactants at equilibrium. Using this equation, we can see if delta G naught is positive, that means K is less than 1. And the more positive delta G naught, the smaller the K. If delta G naught is negative, remember delta is always products minus reactants, and the higher the free energy, the less stable. And so if delta G naught is negative, that means the products are lower in energy, more stable. At equilibrium, we should have more of the products. Remember on the right-hand side, it's all products. Left-hand side is all reactants. The more negative your delta G naught, the larger the K. Now, because you have that exponential, if you change delta G by, say, 40, so 40 kilojoules per mole, that gives you a K of 9.8 times 10 minus 8. We'd call that reactant favored. That would be a non-spontaneous reaction. Remember, delta G naught equals minus T delta S of the universe. If delta G naught is minus 40, that would give us a K of 1 times 10 to the 7th. That would be product favored, and that would be spontaneous. And so there's actually 4 different ways of determining delta G naught. We can do the products minus reactants thing. We can do delta H minus T delta S, which is one of my favorite equations. We can rearrange the equation that we talked about a minute ago, and so we get delta G naught equals delta G minus RT natural log Q. Or we could do delta G naught equals minus RT natural log K. We could also do delta G naught equals minus T delta S of the universe. And so which equation you use just depends on what information that you're given. And so a question we could see would be, what is the Ekman constant for the following reaction? And we're given our delta G naught. And so delta G naught equals minus RT natural log K, which means K is equal to exp minus delta G naught over RT. And so we can calculate our delta G naught over RT. Now one thing you have to be careful is that typically delta G naught is kilojoules per mole. and R is joules per mole Kelvin. And so we have to change the units of delta G naught or for K or for R. And so what I did is I changed from kilojoules to joules. This should be per mole. And so if I move the decimal 1 over 3, that gives me minus 32,910 joules per mole. And so the joules cancel the joules, per mole cancel per mole, per Kelvin cancels with the Kelvin. And so this gives us 13.27 for our minus delta G naught over RT. Now, exponents always have to be unitless. We plug that, we take that to the power of E, and that we get K is equal to 5.8 times 10 to the 5th. And so the more negative your delta G naught, the larger the K. And so there's 3 different possibilities. You can have delta G naught negative, which means products are more stable. So we'd call that product favored. Our K would be greater than 1. We'd also say this is a spontaneous reaction, meaning it can occur without any outside intervention. The boulder would roll down. You can have delta G naught greater than 0, which means the reactants are more stable. Remember, delta is products minus reactants. The higher the energy, the less stable. And so if the reactants are more stable, we'd expect to have more reactants at equilibrium, so that's reactant favored. Our K is less than 1, and we refer to this as a non-spontaneous reaction. If delta G naught equals 0, then K would be equal to 1, and we call that reversible. And so the system will always go to the side with the lower free energy. So true or false, if we make a reaction go faster, we can increase the amount of products at equilibrium. And so you can make a reaction go faster by adding a catalyst, but this is false. Remember, a Eckman constant is a constant for a specific reaction at a specific temperature. And so by using a reaction to make the reaction faster will not change the equilibrium. All it will do is cause the reaction to get to equilibrium faster. True or false, the bigger delta G naught, the larger the K. And so that's false. The bigger delta G naught, the smaller the K. The more negative delta G naught, the larger the K. True or false, if one starts with a higher concentration of reactant, the Eckman constant will be higher. And so that's false. Remember, Eckman constant is the constant for a specific reaction at a specific temperature. Changing concentrations does not affect the Eckman constant. True or false, the reaction free energy at equilibrium is 0. And so that's true. And so remember, the reaction free energy, the non-standard reaction free energy, is just the slope of this line. And so at equilibrium, it is 0. True or false, the standard reaction free energy at equilibrium is 0. And so this one's false. And standard reaction free energy is just the products minus reactants. And so like the Eckman constant, the standard Gibbs free energy is a constant for a specific reaction at a specific temperature. True or false, all reactions stop once equilibrium is reached. And so that would be false. Remember, the forward reaction, reverse reaction are constantly going. It's just that once you reach equilibrium, the rates of the forward reaction equal the rate of reverse reaction, and so that's why the concentrations do not change. True or false, in an equilibrium reaction, the reverse reaction will begin as soon as any products are formed. And so that's true. As soon as you have any products, then you will start getting that reverse reaction occurring. Now, initially, the reverse reaction will be very slow, but as soon as you have any products, it will start to occur. So hopefully you can identify the similarities and differences between the reaction quotient and equilibrium constant. You should be able to write down the expressions for reaction quotients and equilibrium constants, be able to determine the reaction quotient. You should be able to determine how a system will reach equilibrium, if it will form more products or more reactants. If the forward reaction will be faster, reverse reaction will be faster. You should also be able to determine concentrations at equilibrium. I hope that was helpful.